Alright, so we're ready to start. In this video, we are going to recap the absolute Scala essentials that we are going to use in this course. Now, this course will require you to be an advanced, a very comfortable Scala user, so the notions that we are going to discuss in this video might be a little too basic. So if they are too basic for you, just feel free to skip this video and carry on with the next videos. Although I do recommend watching this video even as a refresher, perhaps at increased speed. So, without further ado, let's get to our soon-to-become favorite project in this course. So in our cats project under source main Scala, I'm going to go ahead and create, as is customary for Rock the JVM courses, I'm going to create a new package for this chapter in this course. And I'm going to name this, where'd I go? I'm going to name this Part 1 Recap. And in this Part 1 Recap package, I'm going to create a Scala application that I'm going to call Essentials, or Essentials Recap. I'm going to make it an object, and I'm going to add a main method at the end. Cool. So in this video, we're going to discuss the absolute Scala essentials. Let me collapse my file explorer, and let's start with the absolute very basics: values and variables, which I'm going to erase because we are going to deal with some advanced functional programming stuff. So I'm not even going to discuss variables in this video or in this entire course. We are dealing with pure functional programming, so we are going to rely on immutable, that is constant, values. So define a value, val, a boolean, with the type, boolean, and on the right-hand side of the equal sign, I'm going to give it a value. This is piece of cake. You've probably seen this before. We also deal with expressions in functional programming. So our programs are composed of values and expressions to combine those values and obtain new information. So I'm going to define an if expression, and I'm pretty sure you're well aware of how we define an if expression. We put if and then a condition, 2 greater than 3. Then I'm going to return a value, let's call this bigger, else smaller. The if expression is an expression, not an instruction, because it evaluates to a value. So expressions are evaluated. That is, they're reduced to a value. All right, piece of cake. We discuss instructions versus expressions. And the canonical quote-unquote instruction in Scala is also an expression returning the very special type called unit. So I'm going to define the unit as println hello Scala. The println function is a function that doesn't return anything meaningful. This is the definition of an quote-unquote instruction. However, Scala also encodes this as an expression returning unit. And unit is the equivalent of void in other languages. And unit has no meaningful value. It has the only instance parenthesis parenthesis, which you've probably seen before. So this is the unit value, and all of the functions that print something or show something on screen or write to a file or do any side effects return unit. And we call side effects the kind of actions that do not evaluate to any meaningful value, and yet the computer does something, like show something on screen. So these are the so-called instructions, which in Scala are represented by this unit type. All right, cool. So I hope these all make sense. I'm going to discuss a little bit about object-oriented programming, which is a fundamental building block in basically any Scala codebase. So in object-oriented programming, as I'm very sure you're well aware, everything is an object. That is, we operate with values that are instances of some sort of custom data types that we call classes. So in Scala, we define a class by the keyword class, and then we give this class a name. And a class may contain fields and methods, and if we want to create some type hierarchies, we say that a class cat will extend animal, meaning that it will inherit all its fields and methods that are not private. All right, so I'm pretty sure you're well aware of this kind of class definition, class extension. I'm pretty sure you're well aware of what inheritance means and what kind of fields and methods can be inherited, that is, the non-private ones. And I'm pretty sure you're also familiar with the notion of traits, which are particular to Scala, and a trait is the equivalent of a Java interface, which can contain unimplemented fields and methods. So I'm going to define a trait carnivore, and I'm going to define a method eat with an argument animal, and this returns unit, for example. And I'm going to leave this unimplemented because usually a method would look something like this. You would say equals, and then you would use a single expression, which will give the value of the function when it's being called, but I'm going to simply remove that and leave the method unimplemented. Now, I'm sure you're well aware as well of the inheritance model of Scala, in that a class can extend a single other class, but you can mix in 0 or more traits if you want. So you can extend at most one class, but inherit from at least 0 traits. You can mix in as many as you want. And I'm going to give an example. I'm going to define class crocodile, which extends animal, but it mixes in, this is the term that we use, mixes in the term carnivore. And because I've defined a class here, and I've not marked this class as abstract, meaning that it can hold unimplemented fields or methods, the compiler compels me to either declare this class abstract or implement whatever I left here above unimplemented. So I'm going to define the method eat, and IntelliJ is smart enough to suggest a completion for me, and I'm going to simply print line crunch or something like that. All right, cool. Scala also has this notion of a singleton, which in Scala is called an object, as I declared here above. So if I declare an object my singleton, I've implemented the singleton pattern in one line, meaning that this object can be used as a value, and it's the only value of its type. So my singleton can only contain a single value. However, Scala also introduced this notion that you can declare a class and an object, or a trait and an object, in the same file. This is a pattern called companions. And if I declare an object carnivore, this will be the companion object of the class carnivore. All right, so defining the trait carnivore and the object carnivore in the same file is called companions. And if you define some fields and methods in this object, you can invoke them as carnivore dot and then the field or the method, which looks similar in real life usage as Java static methods or C++ static methods. So this is how Scala organizes fields and methods that are instance specific, such as this method eat, or class that is type specific by defining these fields and methods in their companion object. We're going to use companion objects quite a lot, and in fact we are going to use the apply special method quite often in this course. Awesome, so I'm pretty sure you're familiar with all these concepts. I'm also going to use generics, and we are going to use generics quite a lot. I'm going to define a class, let's call this my list, and adding a generic type is done with square brackets, and you can name the generic type by a single letter inside. So this is in order to reuse the same code on multiple types. For example, the list mechanisms are applicable to any types you might store in a list. If you store ints or strings or persons or singletons or animals or what have you, the mechanism for a list is identical, so it's worth having my list generic in this sense. And we're going to use generics quite a lot. Cool, let's talk about other things. I'm going to talk about method notation. So I'm going to define a value, let's call this 3, as 1 plus 2. This is a simple expression with 1 plus 2 with the operator plus in between the operands 1 and 2. But what if I told you that if I defined an alternative 3, the operator plus was a method on the int type? Pretty sure you've seen this in the Scala beginners and advanced courses. So the expression 1 plus 2 is equivalent to saying 1 dot plus with the argument 2. So every single method that has a single argument can be infixed like that. And we might see this in practice. And as I'm sure you're well aware, Scala is very permissive when it comes to variable, class, or method naming. In this class, we have a method called plus, and we might see some weirdly defined methods in the rest of this course. Cool, so this is the infix method notation. Scala also offers prefix and postfix method notations, which you can find more details in the Scala beginners course. Cool, let's talk about functional programming. So the goal of functional programming is to be able to work with functions as we work with any other kinds of values like numbers or instances of classes. And to that end, Scala can define function values that it can pass around or return as results. So I'm going to define a function value that I'm going to call incrementer as the type of function that takes an argument int and returns the value of type int. So this is the function type that would take an int argument and returns an int result. And on the right hand side of this declaration, I'm going to define a anonymous function. So I'm going to define x arrow x plus 1. And this is how we define an anonymous value in Scala. And the type of this argument x is automatically inferred by the compiler because I've declared the type of this incrementer function beforehand. So the compiler can infer that x is of type int. Now, having defined this kind of function, we can use it to either return some results by shoving some values into it and calling it by saying incremented as incrementer applied to, let's say, 45, and we obtain the value 46, obviously. Or we can pass it around in what we call higher order functions. The higher order functions are the kinds of functions that receive other functions as arguments or return other functions as results. This is one of the crux aspects of functional programming. And the classical higher order functions that we use the most often in functional programming is map and flat map. And if we operate with collections, we quite often use the filter higher order functions as well. So let me define a processed list as list123.map, and this map receives a function from int to some other type argument b, and I can pass in my incrementer function, and this would be all right, and this will be the list of 234 because the function incrementer is applied to every single element in the list. Now, flat map is very interesting because it defines a pattern on many kinds of collections and many other kinds of data structures, and I'm going to define a longer list as list123.flatmap, and flatmap takes a function from an element to something that returns another collection. So I'm going to supply a function x arrow list x and x plus 1. That is, for every element x, the function will return the list containing two elements, the argument x and the argument x added with 1. And all these small lists will be returned from applying the function to every single element, and all of these small lists will be concatenated in the final result. So the final result of this expression is going to be list of 1, 2, 2, 3, and 3, 4, because the list 1, 2 was obtained by applying this function to element 1, the other small list was obtained by applying this function to element 2, and same for element 3. And all these small lists are concatenated into one big list. And flatmap is very widely used for this kind of scenarios. Let's move on. I'm going to discuss options and try. So let's talk about options first. Options are a data structure that might or might not contain a value. Let me define val an option as option, and here you can pass something that might be null. And I'm going to pass here the value, let's say 3. So when I say option with the argument 3, I'm actually calling the apply method of the companion object of the option abstract class. And the apply method returns an instance of type option int. So this will be an option int. But the apply method will return an actual instance of a subtype of option int. And option only has 2 subtypes. They're called sum and none for the situation where you have or you don't have a value. In this case, we will have sum3. And options are particularly valuable because we can operate with options as we would on lists, regardless of whether they have a value inside or not. And options are valuable in this sense because they prevent the kind of defensive null checking that we used to do in other languages like Java or C++ or things of those sort. So if I define a doubled option of type option int, I would say an option, and I would call the map method as I would on a list, and I would say underscore times 2, which is shorthand for x arrow x times 2. And this kind of expression would work regardless of whether an option actually has a value inside or not. If it does have a value, then that value will be multiplied by 2 and that value will be stored in the final option. If the original option doesn't have a value, then the result is also empty. All right, so this is how options work, and they're particularly convenient for functional programming because we can apply these higher order functions on them. All right. In a very similar fashion, tries serve the same purpose, except in this case, try all encapsulates the kind of expression that might throw an error. So I'm going to define an attempt as try, and I'm going to need to import try. I'm going to hit enter so that we import Scala util try, and the try apply factory method will take an expression which might throw. So you will put here something that might throw, and here I'm going to return 42 or something like that. And in much the same fashion, try has 2 subtypes. It'll have a success, in this case a success of 42, or in the case that the expression that I pass inside throws an error, then we will have a failure containing that exception. Now, try works in a very similar way to options or other kinds of data structures, in the sense that try also has functions like map, flat map, filter, and so on and so forth. So if I define a modified attempt as an attempt.map underscore plus 10, this map function will operate in the following way. If the attempt contains a regular value, that is a success, then its value inside will be added with 10, and that will be stored in the final data structure. If the original data structure is a failure with an exception, then that same exception will be stored in the final try. And this is of type try int. Okay, we're going to use these kinds of values throughout the course. Good. Let's talk about another thing, which is pattern matching. This is one of the most powerful Scala features, and it's much more than a switch on steroids because it allows decomposition of certain values. So if I define an unknown of type any, and let's give this a value 45, then I can do, let's call this ordinal as an unknown match. And then we can add a bunch of cases which can return different expressions depending on whether this value matches any of those patterns. So if an unknown matches the case 1, so that is the pattern where the number is equal to the number 1, then I'm going to return the string first. In case the pattern matches 2, then I'm going to return second. And in case we match anything else, I'm going to return unknown. All right, so this is the kind of switch on steroids. However, we can also define an option match, And in this case, we can decompose this option. And if I use the case sum value, and then I can use this value in the expression that I return on the right hand side of the arrow sign. So the option is not empty, and then I can inject the value here, or I can say case none, and I can say on the right hand side the option is empty. All right, so let's call this option description. So this option description is a string, and the value of the string is one of the expressions here on the right hand side of the arrow signs, depending on whether the argument and option matches any of these patterns. All right, so pattern matching is really, really powerful. I'm pretty sure you have quite some experience with it. All right, one other important thing that you are surely going to come across in your Scala experience is asynchronous programming with futures. So futures are data structures whose values are computed on some other thread at some point in the future. This is why they're called a future. Now, futures will need an implicit execution context. The execution context is a data structure that will hold the mechanism for scheduling threads. So in previous courses and in previous Scala versions up to 2.12, we would say import Scala concurrent execution context implicits global. However, in Scala 2.13, the implementation of the global execution context was changed to save some future spawning overhead, and as such, nested futures will not run in parallel unless we use the blocking API. This, in my opinion, is a wrong trade-off. So starting from now, from Scala 2.13, I am not going to advocate, I'm not even going to mention the global execution context. Instead, I'm going to define my own execution context whenever we use futures. So instead, I'm going to use an implicit val, and we're going to discuss implicits in a subsequent video. Implicit val, I'm going to call this EC of type execution context. Right? And I'm going to spawn an execution context myself as execution context from executor service, and I'm going to start a thread pool which will serve as a platform for this execution context. So I'm going to say executors. This is a Java API, so I'm going to use executors, new fixed thread pool, and I'm going to pass in 8. For example, I'm going to use 8 threads for this execution context, which will be more than enough for what we need in this course. Then I'm going to define a future, and we can spawn a future by calling the apply method of the companion object of the future type. So I'm going to say future42, or and let me import future by hitting Alt Enter or Option Enter on Windows, or by the curly brace syntax, which does the same thing. So we are going to use future, and then I'm going to start a code block, and this code block will serve as the argument of the companion object's apply method. And here we are going to write quite a bit of code. Right? Now this value here, which is the value of the block, will be evaluated on another thread. Now, in order to operate with this feature, you can use the onComplete function. By saying a future.onComplete, and then you would use a partial function, which is basically a pattern match. So you would say onComplete, and the onComplete receives a try object, the kind of try that we wrote earlier, and by using this partial function, we're decomposing it with a pattern matching. So I'm going to say case success with some sort of value. So I'm going to import scalutil success. So if this try object contains a value, then I'm going to print line the async meaning of life is, and then I'm going to inject value here. And in case I have a failure with an exception, which I'm going to import by using scalutil, I'm going to print line meaning of value failed, and I might inject the exception inside. So this block over here is called a partial function. I'm going to talk about partial functions in just a couple of seconds, but let me finish the future API. So one way of operating with futures is by doing this onComplete thing, or you can treat it like a data structure very similar to option, try, list, and other collections, and use map, flat map, and or filter or other functions. So you can say, let's call this another future or improved future, or name it however you want. And I'm going to say a future dot map, and then I can pass in a function _+1. And this will be a future containing the value 43 when it completes. Because all the functions that future supports are being evaluated on another thread, including onComplete. So onComplete is also evaluated asynchronously. Now, I've talked a lot about map and flat map on a variety of data structures. Scala offers a syntactic sugar to compress chains of map and flat map with what we call for comprehensions, which I'm pretty sure you've seen before. So let me introduce for comprehensions here. So I'm going to define a checkerboard as having all the combinations between a list of 3 numbers and a list of 3 characters. So I'm going to say list 123 dot flat map, and for every number inside I'm going to say list A, B, and C dot map, and for every character I'm going to return the tuple, the number, and the character. So this will be a tuple containing on the first member the number, and the second number on the second member the character. So this will be the Cartesian product, all the combinations between these 3 numbers and these 3 characters. So I'm going to obtain the tuple 1a, 1b, 1c, 2a, 2b, 2c, and 3a, 3b, 3c. These chains of map, flat map, and or filter might be a little hard to read, especially if you have lots of them. And so Scala has this for comprehension expression to collapse these map and flat map chains into one very readable expression. So let me define another checkerboard as for, and I will open and close some curly braces, and inside I'm going to say n in. So I'm going to read that as in with a left thin arrow in list 1, 2, 3, and every character in list with A, B, and C. And I'm going to yield, this is the structure of a for comprehension, the expression which will contain all the combinations between N and C, and I'm going to say N and C. So this is an equivalent expression. For comprehensions are collapsed by the compiler to chains of flat map and map, and this is available for any data structure that supports map and flat map. So not just for collections, but also for options, for try, for future, and as we will see later, other data structures as well. Now, I'm scrolling down because I promised I would talk about partial functions. So let me define a partial function as a partial function from int to int. So this is the type of partial function that takes an int as an argument and returns an int as an argument. Now, the difference between partial functions and regular functions is that partial functions do not accept any argument of type int. It only receives arguments that satisfy some patterns. So they are based on pattern matching. So if I wrote case 1 and I return 43, in case I receive the argument 8, I'm going to return the value 56. And in case I receive the argument 100, I'm going to return 999. These are all the values that this partial function will support. If you pass anything else to it, then you will receive a match error because the argument doesn't match any of these patterns. So it's as if you wrote x arrow, x match, and then you would pass in all these cases. We talk more about partial functions in the advanced Scala course. So if you see something like this with curly braces and just cases, then this is a partial function. And this is what we use here with future onComplete. All right, cool. So these are partial functions. And some more advanced bits. And in particular for cats, we are going to use some higher kinded types. And I recommend that you refresh your memory on higher kinded types towards the end of the advanced Scala course, but let me refresh your memory on the most fundamental concepts. We can define traits, classes, or abstract classes that have a generic type argument which itself might have type arguments. So I'm going to define a higher kinded type, and I'm going to type it with a type argument f, which itself has a type argument. So we denote this as f underscore. Just as an example, let me define a trait, let's call this sequence checker, with f, which itself is generic, so it's higher kinded, and this trait, let's say it has a method is sequential, which returns a boolean. Okay, now if you were to use this higher kinded type in real life, you would type that to a type argument that itself is generic without also giving it the generic argument. So if I define a value, let's call this list checker, this will be a new sequence checker with the type argument list. So notice that I'm not typing the list with any other type argument, not list int, not list string, list person, list animal, or something like that, just list. So f here, the generic type argument, is equal to list. And I will define the method is sequential to true, for example. All right, so this is how we would use a higher kinded type in real life. And throughout the cat series, we're going to use higher kinded types a lot. All right, these are the fundamental Scala features that we are going to use in this course. All right, so this was a quick recap of the fundamental Scala features that we are going to need in this course. Now join me in the rest of the chapter because we are going to stress some advanced Scala bits that we are going to desperately need and heavily use in the rest of this course and of the series.